Hello, this is Nick of Time. Welcome to this 12th talk in this series about time and how time is treated by currently accepted theory and how it can go beyond that treatment and improve it. Okay, we have been talking about how special relativity treats time and the logic of the special relativity time dilation equation and its interpretation, and the limitations of the time dilation interpretation. Now we're going to go to part 2 of this series of talks and focus on the empirical data on clock rates as a function of velocity. And section 1, that's this talk, is going to be about the global positioning system's data and what it has to say on that topic. Again, the previous talks have shown that special relativity time dilation equation cannot describe proper time rates, in particular physical changes to proper time rates. Now, our conclusion of this talk, which I'll present up front, and then we'll go through the details of how we get to that conclusion, we're going to show that GPS data by the ton shows that atomic clock rates change as a function of velocity. Further, it's a function of absolute velocity rather than relative velocity. So we have 2 levels of incompatibility between the GPS data and special relativity. Hence, a new cause for this velocity effect on clocks must be found. Can't be explained in terms of special relativity constructs. We have to go and find the real cause. Let's do a quick review of the GPS system. It's used by most everybody worldwide. There were a set of GPS stations located various places on the surface of the Earth. However, people who are on the Earth will not have line-of-sight communication with those stations and hence can't really communicate with those stations. Therefore, to use it as a navigation system, people traveling on the Earth must really communicate with a satellite, which in turn communicates with the GPS stations on the surface of the Earth. So those GPS stations on the surface of the Earth, the clocks they use are synchronized using the Earth-centered, Earth-fixed frame, the EC-EF frame. Now the GPS clocks in the GPS satellites have to be synchronized with those earthbound clocks as well. Now the GPS satellites are not geostationary. They do not hover over a specific spot on the Earth. They orbit the Earth. So, to synchronize those clocks, they have to take into account the velocity effects of those satellites relative to the velocity effects on the clocks on the surface of the Earth. Now the clocks will all be set to universal time coordinated system. Just some general comments about the exposition. The GPS system is a real-world system that works to high precision, and hence there are a lot of real-world problems and real-world complexities. We won't ignore those complexities when we do the analysis, but for this exposition, we'll try and keep things simple and not go into every single detail. For example, the GPS clock rates depend on velocity and on gravitational potential, where we're focusing on velocity effects on clock rates. So we'll focus on that, and we'll not talk about the gravitational potential effects, at least not much. But that does not mean that we're leaving gravitational potential effects out of our analysis. That's part of our analysis, but we'll just focus on what the data is telling us about velocity effects. In addition, the GPS satellite clock rates are adjusted to equal the earthbound clock rates. So we won't mention that if we're talking about the satellite clock rates are slow with respect to the slowed by their velocity. That's already adjusted into the clock rate of the satellite system. So we're not ignoring that fact in our analysis, but we won't give the parenthetical clause each time we talk about satellite clock rates. Hence, as we say, to simplify the exposition, we'll just focus on what the data tells us about the velocity effects on clock rates. Okay, it's pretty simple. Satellite atomic clocks are adjusted to have the same rates as earthbound clocks. Again, the earthbound clocks have been synchronized in the ECEF frame. They're synchronized by accounting for velocity and gravitational potential. Again, we won't talk much about the gravitational potential. The fact is, those clock rates are adjusted by accounting for their velocity. That means GPS depends on adjusting the physical clock rate, the physical proper time accumulation rate of those clocks. And hence, GPS has a problem for special relativity time dilation, because in our previous talks we showed we had 3 levels of problems, and we showed that special relativity's time dilation can't be interpreted as describing proper time rates. You come to contradictions. And again, the problems are so deep that we can accept many erroneous relativist rebuttals and still come up with contradictions. 3 levels of contradictions. Some of those levels have multiple reasons why they're contradictory, why there's a big problem for special relativity. So, we've come to the conclusion, very quickly, very simply, that special relativity time dilation is not being used in GPS, because GPS is built on adjusting for physical changes in proper time accumulation rates based on velocity, as well as other effects. Very straightforward. No one can argue with that. And yet there's another problem. Even if the relativists insist that the time dilation equation can be used to describe proper time accumulation rates, there's still another level of problems. Let's look at that. Okay, the velocity of the earthbound and satellite clocks are used relative to the ECI frame, the Earth-centered inertial frame. You take the center of the Earth and you have a non-rotating frame. And then one uses a ratio of the velocities of the satellite GPS clocks versus the earthbound GPS clocks. And you calculate to determine the adjustment needed for the velocity effect. Thus, special relativity's relative velocity between the two sets of clocks is not used, but rather an absolute velocity with respect to a single frame is used. Thus, the special relativity model is not used, but instead, the Lorentz relativity model is used. Okay, we'll look a little at that a little deeper. Using a third-party frame really is not part of the special relativity model for looking at clock rates. Remember, we're accepting the special relativist claim, saying that special relativity time dilation describes proper time rates and changes in proper time rates as a function of velocity. Now, here this little diagram below says we have C at rest in a specific frame. Let's call it the Earth-centered inertial frame. And A and A's clock is moving off to the left with velocity v with respect to C. And B and B's clock is moving off to the right at velocity v, the same velocity, but in the opposite direction, with respect to C. Now let's use special relativity's time dilation equation. Well, A would say, if we're interpreting time dilation as changing clock rate, A would say that B's clock is slower than his own clock, A's clock. Conversely, B would say that A's clock is slower than his own clock, B's clock. And someone in the third-party frame would have a different view. In this case, C would see both A and B moving away with relative velocity v. So C would conclude that both A and B's clocks slow down relative to its own clock by the same amount, and therefore would conclude that A's clock and B's clock are running at the same rate. So that's a third conclusion, a third contradictory conclusion. And if you had another third-party frame, D, that would say moving at half V to the left, D would come to a fourth conclusion about the relative rates of A and B. So you can't arbitrarily choose the third party frame to do calculations on the rate of A versus B. In fact, the only frame that you could choose that would be high precision and moves very close to that frame would be a frame that is the preferred frame in a Lorentz relativity system, where there physically was a preferred frame. And then the special relativity equation would work out because the relative velocity with respect to that preferred frame is also the actual absolute velocity. So if you've chosen a third-party frame and the system works to high precision, that shows that you're in a preferred frame system and that you've accurately located the preferred frame. In this case, at least in the vicinity of the Earth, the ECI frame would be the preferred frame or very, very close to the preferred frame. Your degree of precision and accuracy would say how close you are to having determined the actual preferred frame. So, let's look at the special relativity model and GPS. By our previous talks, we know that special relativity time dilation does not describe proper time accumulation rates. So otherwise, there's an obvious contradiction. You determine that A's clock is slower than B's clock, and B's clock is slower than A's clock, and that's not just counterintuitive, that's counterlogical. So, in special relativity, in special relativity, one cannot arbitrarily choose a third-party frame to determine the time dilation effect between clocks in two other frames. And you can't do that because one would get different contradictory results depending on which third-party frame was chosen. So, our conclusion. GPS is a widely used system that works to high precision based on the Lorentz relativity preferred frame model, with the ECI frame as the single preferred frame. And the GPS data on proper time accumulation rates as a function of velocity is not consistent with the special relativity model. And this is very simple to see, and I'm sure that the relativists can come up with arguments, but to come up with reasonable arguments is very difficult. You can't argue that the clocks are adjusted, the proper time rates are adjusted, and right there that rules out special relativity's time dilation. Further, we conclude that GPS data is also not compatible with a just observed interpretation of special relativity time dilation. Because just observed interpretation means that the observations would have to be symmetric, whereas in GPS, the observations, the communication between the two sets of clocks, is symmetric only because the clocks are manually adjusted to be different rates, which would show that the clocks are actually not symmetric. The non-adjusted clocks would would not be symmetric. If you have an asymmetric difference, that means there's a physical difference in the clock rates. GPS data is also not compatible with special relativities. All inertial frames are equal, because one would find that if you picked another frame other than the ECI frame, when it was significantly different, then the GPS system wouldn't work. You have, again, cars going into lakes or going into someone else's kitchen. So, special relativity's model of time is inconsistent with GPS's empirical data. Very important conclusion. This topic really gets me pumped up. It's very powerful. Okay, you might say, well, why should I listen to you? Nick of time, you're a nobody. Well, I might say, well, that's an excellent point. So let's call in a world-renowned expert on navigational systems, in particular the GPS system, which is a navigational system, Ron Hatch. He's a holder of over 30 patents for the GPS system. He knows the GPS system really well, and he knows the GPS data as well as anyone on the Earth, and he also knows other systems like DVLI and the NASA navigation systems. He says, rather than supporting relativity theory, GPS actually reveals flaws in relativity theory along the lines that we've been talking about. He's reviewed what I say and concurs with what I have presented here. Okay, so what's next in our series of talks, particularly in part 2 here? Well, we'll talk about the 3 other main sources of data, empirical data, on clock rate as a function of velocity. Talk about particle accelerated data, decay rate for muons that are created in the upper atmosphere, and the Haffler-Keating experiment. We'll also talk about why the empirical data on proper time accumulation rates has not been correctly interpreted. That's a major issue unto itself. So, thank you again for joining us for this 12th talk, and I hope to see you all for the 13th talk.